Welcome. In this video, we're going to go over a few practice problems related to rate laws and also using the method of initial rates to determine what the reaction order is. Here is our first problem. So we're looking at a reaction between nitrogen monoxide and hydrogen gas, and we're given the rate law for this reaction. And the question is, what is the reaction order with respect to nitrogen monoxide, and what about hydrogen gas? So this question is just trying to assess whether you know the vocabulary here. So this is a generic rate law. It's rate equals some constant K times the concentration of the reactants to the power of some exponent. And these exponents right here are what we call the reaction order. So in order to find the reaction order, we're going to go and look at what the exponent is in the rate law. So for NO2, the exponent is a 2, so that means that it is second order with respect to NO. The H2, if there's nothing written, that means that it is first order. So usually if the exponent is a 1, we just don't write it. So since there's nothing written here, that means that it is first order. The overall order of the reaction, you get this by adding together the reaction orders of the reactants. So this one is third order overall. So the individual reaction orders will never be larger than 2, but the overall reaction order can be greater than 2. Here's another problem we'll take a look at. Here is our reaction, and here is our rate law. So first question is, if the concentration of B doubles, what will happen to the rate? And in order to figure this out, we need to look at the rate law. So the rate law tells us that the rate is proportional to B squared. So we know that rate is some constant K times B squared. So let's think about what would happen if that concentration doubled. So instead of B, I'm going to write this as 2B. So we can simplify this and say, okay, this is the same as K times 4B squared. So notice that when we, sorry, I can't write and talk at the same time. Okay, so notice that when we double the concentration of B, the rate will go up by 4 times. Okay, another way of thinking about it is that the rate is, proportional to B squared. So if we double the concentration, the rate is going to go up by 4 times. That's another way I like to kind of write it out there. So either way, however we think about it, the key thing is that B is second order. And that means that if you double the concentration of B, then the rate will increase by 4. So the rate will be 4 times faster. That is the answer to this problem here. So the reaction orders for A and B. B has a 2 by it, that's its exponent. So we'd say that B is second order. And then A, notice that A does not even show up in the rate law. That is because A is 0th order. So if a reaction does not show up, that means it's 0th order. And that's the reason why it doesn't show up is because anything to the power of 0 is just 1. So you don't even see it in your rate law. So we'd say B is second order, and then A is 0th order. And now let's take a look at how we could solve for K. So here's our equation, rate equals KB squared. This is an equation, we can do some algebra with it, so we can rearrange and solve for K. So K equals rate divided by B squared. We are not given numerical values for these numbers here, but we do know what the units typically are. So we know that the rate is measured in some molarity per time. I'm going to assume that it's seconds because that's the most common one. And then the bottom, whenever you see these square brackets, this stands for concentration of. So this is measured in molarity. So the top is molarity per second. The bottom is molarity squared, so that's molarity times molarity. So notice I've got molarity on the top and the bottom. So we're going to cancel one of those m's out. And you're left with 1 over second over molarity. We can consolidate that and say 1 over second molarity. And you could also write that as s minus 1, m minus 1. These two are the same thing. So either one of these would be an acceptable way of writing this unit. I tend to write them this way. In the AP test, you tend to see the use of these negative exponents. Either one of them is fine. You just want to be comfortable understanding what these negative exponents mean and know that this is the same thing as this. So let's take a look at a problem with a data set. So we've got a reaction right here between ClO2 and the hydroxide ion. I'm trying to figure out what the reaction order is for these two reactants based on the data. So remember, we can never figure out the reaction order just by looking at the balanced chemical equation. We need to actually collect some experimental data. And this is showing, in this problem, we're doing this using the method of initial reaction rates. And what that means is that we're going to set up several experiments where we just change one variable at a time, and we look to see what impact that variable has on the initial reaction rate. So first we have to just kind of interpret our data set. So if we want to find out some information about ClO2, we want to compare two reactions or two experimental setups where the only variable that changes, the only variable changing is the concentration of ClO2. So if I look at my data sets, it looks like in experiment 1 and 2, the concentration of hydroxide is staying about the same, but the concentration of ClO2 is double in experiment 1 than what it is in experiment 2 here. So when the concentration of ClO2 is, so let's take a look at this way. So when we go from experiment 2, when we compare experiment 2 to experiment 1, in experiment 1, the concentration of Cl2 is twice as much. So now let's compare these reaction rates. I'm going to figure out how much faster is the reaction. So what I'm going to do is I'm going to take this faster rate and divide it by the slower rate to figure out what, how much faster it is. And so when I divide those, I get 3.9 when I plug that in my calculator. So it's about 4 times faster. So if I look at experiment 1 versus experiment 2, what I see is that when the ClO2 concentration doubles, the rate quadruples. And then we need to ask ourselves, what scenario does this fit with? So we just have 3 options here. The ClO2 is either going to be 0th order, it's going to be 1st order, or it's going to be 2nd order. So those are my 3 possibilities. So let's think those through. If it were 0th order, then if I doubled the concentration, the rate would stay the same because 2 to the 0th power is just 1. So it'd be unchanged. If it were 1st order, then if we double the concentration of Cl2, I would expect the rate to also double. If it were 2nd order and we were to double the concentration, we would expect the rate to go up by 4 times as much. And it seems like this is what happened here. When we doubled the concentration, the rate went up by 4 times. So that tells us that, that it is 2nd order with respect to ClO2. So I'm going to write up here, second order. And now let's take a look for hydroxide. So again, I want to find two data sets where the only variable that changes is the hydroxide ion concentration. Let me maybe write with a different color here. So if I look at experiments 2 versus 3, so we're going to compare experiment 2 versus experiment 3. Notice in those two experiments, the amount of ClO2 stays the same, but in experiment 3, it looks like the concentration of hydroxide has tripled. Right, so experiment 3, the concentration is 3 times greater than it is in experiment 2. So now I want to see what impact that has on the rate. So again, I'm going to take my faster rate and divide it by my slower rate. So I'm going to take 0.0218 divided by 0.00733, and I'm going to see what I get here. So I get like 2.97. So it is about 3 times faster. Okay, so when I triple the concentration of hydroxide, the rate triples. So again, let's think through our scenarios here. The rate, it is either, the reaction order for hydroxide is either 0th order, it is first order, or it is second order. And if we think through these scenarios, if we triple the concentration and it's 0th order, the rate's going to stay the same. So if something's 0th order, it's not going to impact the rate. You could make it 100 times more concentrated and the rate will not change. If it were first order, then if you triple the concentration, it would triple the rate. And if it were second order, if you triple the concentration, the rate would go up by 9. So what happened here is that when we tripled the concentration, the rate also tripled. So that fits this scenario right here. So we would say that the reaction is first order with respect to hydroxide. Okay. Now I'm going to pause real quick and erase some of this. Okay, so if you need to go back and look at this again, you could always rewind the video, okay, because I need to give myself some more space here. So we figured out what the reaction order is with respect to my two reactants. All right, thanks for your patience as I do this. Okay. And now we can write the rate law, and we can actually figure out the value of K here. So this will be our first problem. We're actually figuring out a value of K. Okay, so the rate law is going to be rate equals some constant K times ClO2 to the power of 2 and hydroxide to the power of 1, because we said ClO2 is second order, hydroxide is first order. And typically, we won't write the 1 there. So we will usually see it like this. This would be a rate law. If you leave the 1 in, that's totally fine too. So that's the rate law. The overall reaction order you get from adding up the exponents. So it is third order overall. And now let's find the rate constant. So what we're going to do is we're going to take this rate law, again, which is rate equals K times ClO2 squared times OH, and we're going to rearrange it to solve for K. So K equals rate times ClO2 squared times hydroxide. And then we're going to actually plug in some values from our data set. And it doesn't matter which set of data we use. You can use experiment 1 or 2 or 3. The idea behind K is it is a constant. So no matter which set of data you use, you should end up getting the same value here, as long as we are carrying out these reactions at the same temperature. Because K, it turns out, is temperature dependent. But we're assuming we're carrying all these out at the same temperature. So I'm going to use experiment 1. So I'm going to say the rate is 0.0288. molarity per second. And then the bottom, I've got 0.050 molarity squared, and I've got 0.050 molarity over here. So what I'm going to do is I'm going to first plug these numbers into my calculator. So 0.0288 divided by 0.05 squared and 0.05. If I plug that in my calculator, I should get 230. That's rounded to 2 sig figs. If you're wondering if yours looks a little bit differently, that's why I wrote it like this. And then I'm going to write out some work for the units here. So if I look at the units, the top is molarity over second, and the bottom is molarity squared. So that's molarity times a third molarity. So there are 3 molarities on the bottom. So if you square this value, the unit also squares. That's important to keep in mind. So I've got 1 molarity on the top, so I can cancel out one of those molarities on the bottom. So what's left is the top is 1 over seconds, so it's like an inverse second, and the bottom is molarity squared. So I can write that as 1 over seconds times molarity squared, or I can write this as S minus 1 M minus 2. Okay, so that's the units of this rate constant is S minus 1 M minus 2. And the units of the rate constant are going to vary based on the overall reaction order, right? So it depends upon how many molarities are on the bottom here. So maybe we got 2 molarities on the bottom, or 3 or 4. It depends upon what this reaction order is. So the units of the rate constant, it's not something you memorize, it's something you just figure out by doing the math here and just plug in those units in here and looking for things to cancel out. All right, so please send me a message if you have questions. Thanks for watching.